Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, maximum sum circular subarray. So we get an integer array of numbers of length n, and what we want to return is the maximum possible sum of a non-empty subarray. This part is important. But what do they mean by circular here? So what they mean by circular is that the end of the array can connect to the beginning. So you can think of it like a sort of a linked list where this connects to the beginning. And the only constraint is that since it's a subarray of this array, you shouldn't have duplicate elements. What do they mean by that? You can't just include, let's say, -2 here, right? And because this -2 connect to this -2, you go to 1 and then you go to -2 again, and like this. So in this case, you have -2 two times. That's not allowed, right? It needs to be a valid array, but you can think of it sort of like this one here is connected. The last one is connected to the last element is connected to the first, but still a subarray is a subarray where you don't duplicate an element at the same index multiple times. So that's what the whole thing here says. So how do we solve it? So let's see these couple of examples here first. So for the first one, it's 3 because, well, if you take any other one, if you take -2, 1, you get -1. That's not bigger than 3. -2, 3, that's 1. That's not bigger than 3. You could try all the combinations possible. 3 is the maximum. This one, and you can see here 3 is right in the middle of the array, right? It's actually the same as the maximum subarray if we didn't have this this thing where the last one is connected to the first one. The second one, the max is actually on the edges, where we use the fact that the last one is connected to the first one. Okay, so you can sort of see here that there are two cases, right? One where it's just like a normal subarray, it's somewhere in the middle, or it can be the entire array even. Another one can be where it's just we use the connection of the last element to the first, right? So yeah, let's see how we can solve it. Okay, so how do we solve it? So the way a lot of people you will probably find explaining on Leetcode and on YouTube is using the min subarray approach. I find that one more advanced and a little bit harder to understand. So I'm going to try a different approach here. Maybe I will do a different video on that one, but I'll try to explain here a different solution that I think is easier to understand. So what are the cases that we can have where we have in this problem here? So let's say we have our subarray like this, right? What are the cases that we can have the max? Well, it's either the entire array. So the case one is the entire array is the maximum subarray, right? That can happen if all of the elements are positive, right? What is the other case? Another case is maybe it's just some prefix of the subarray of the array is the prefix sum, right? Okay, what is another case? We're just going to list all cases until we see a pattern. So another case, it can be just the suffix of the array is the max subarray, right? An example here, it can be, let's say the first part is all positive numbers and the last part is all negative numbers, right? This is just an example. It doesn't have to be all positive in the prefix, right? The prefix is still a max this way, right? The other case here, again, we could have something like this, -3 and then 1, 2, 3, and this is an example of that case. Another case is we could have something like this, and the maximum subarray can be the elements in the middle. Again, another simple example can be -2 and then 4, 5, 6, and then -4, -5, something like this, right? Or even just -5 here. We'll remove this, right? So this is also a valid thing. And all of these cases, by the way, if you notice, can be actually condensed into one thing. This is as if we didn't have a circular subarray. This is as if we didn't have the connection here. If the maximum subarray is one of these cases, we just need to run the maximum subarray normally without taking into account that the last element is connected to the first element, right? Without taking into element the circular approach, the circular property of this specific problem, right? And so this is also a good thing to think about, is whenever you have a problem, you decompose it into multiple cases. Try to see if you have a lot of cases, try to see if they can be condensed into one case. Okay, so here we can see that 1, 2, 3, 4, same case where we can just find max subarray. We will call it normal. Find normal max subarray, right? And by the way, this can be solved with Cadena algorithm. I can quickly go over it in a moment, but it's a known thing. There is another Leetcode problem that has this exact problem. Okay. Now, what are the other use cases that use the fact that you could go from here to here? So that one, let's call it case 5. You could have something like this, right? Where actually the max subarray is this portion, the suffix portion with the prefix portion, and that's one of the examples we have. Example 2, which is 5 minus 3, 5. So this array, the max is actually just this portion with this one, right? So you can think of it like the array is sort of like this, duplicated, but you shouldn't have the same element twice, right? So 5 minus 3, 5, and this is the max subarray. So it's 10 here, right? So this is an example of this use case, right? And this is the only possibility, right? Because let's say, for example, you had something like this entire subarray, right? And we didn't, by the way, in this case, I didn't specify which position. Maybe between them there is only one position. But if between them there was no position, right? Let's say all the way to here, and then this one is all the way to here, then that's the exact same thing as the entire array, right? That's the exact same thing as the first case, right? So the only case we need to handle that is not the normal one is that basically the maximum sum, right, is a sum of a prefix, which is here, this is the prefix sum, and the suffix that don't overlap, okay? It can be even like the prefix sum is here and the suffix sum is here, right? Even though this is similar to this one, we can still take it because it will start at the end, so it won't be the value will be the same, but it won't be the same structure, but we can still take it. But the only thing is that it shouldn't be that we can't have it so that let's say something like this. So this would be our prefix sum, and let's say maybe this would be our suffix sum. We can't, this is not valid because we will be counting this portion twice. And so what is the constraint that we have here? So it's the sum of prefix, let me take the same color. So it's sum of prefix plus sum of suffix, right? With constraint that prefix and suffix should not overlap, right? And suffix should not overlap, because if we overlap, we will count the same number in the same position twice. Should not overlap, okay? So, okay, so now we know the two cases we need to handle. These cases all are the same case for normal max subarray. We can use Cadena algorithm to solve this. It's just normal Cadena algorithm. And so now conceptually, the only thing left to do is handling this case. How do we do it? So to handle this use case, you can see already, well, we need to know the prefix sum for each position I. So for each I, just take the prefix plus the max suffix we can take, right? Okay. Basically, for each I, we will calculate the prefix, but we need to know what's the max suffix we can associate with that I to get the max sum. You may say, okay, why don't we take the max prefix? Well, if we, for all the i's, for all the possible prefixes, plussing them with the max suffix, that is not overlapping, of course. If we take the max of all of these, that is almost like that's actually the same as taking the max prefix. It's just we will do it over time with this I. I hope that point was clear, right? And so what this would mean is that we just can do two passes. One pass is to store all the max suffixes for each position. So maybe we'll call it right max. Okay, so we'll fill this list with basically the max starting at position I to the end. That's what right means. And then from there we can do a pass to do the prefixes. And for each prefix, let's call this case where the sum is prefix plus suffix. I'm going to call it edges sum, because it's just the sum of the edges, right? And so the edges sum each time is going to be just the prefix sum at I plus the suffix sum, the max suffix sum starting at I plus 1, right? Because remember, we don't want them to overlap, and so we can't do the max right sum at I, because then we will overlap at I. We want the max right sum at I plus 1. So this would be right max at I plus 1. Okay? So that's the main idea here. Now let's run it on an example first to make sure it works properly. I'll start with the example where we actually have a valid case. We actually have this case, so that would be this one here. So let's run it on that one. So it's 5 minus 3, 5, right? So this is the array we have. So what do we need? We need first to calculate this right max, which we said is just the... So for each position, we needed 4, 0, 1, 2. Is going to be the max sum in array starting at I. Starting at I, right? And so first so that means we can go from right to left so that it's easier, right? And so for 2, it's just the same value. So for the last one, it's just the same value, it's 5. Now for minus 3, what's the max sum? Well, we need to keep track of the suffix sum overall, going left to right. So the suffix sum initially, right now, it's equal to first 0. And then when we process 2, it becomes 5. And then when we go to minus 3, it becomes 2. And so here we check, is 2 better than 5? We compare suffix sum with the at right max at I plus 1, right? So basically, it's either we take the element at I or not, depending on whether that will give us a better sum or not. And so we compare 5 and 2. 5 is better, so we put 5. And now we go again here. 2 plus 5, that's 7. 7, the max between 7 and the right max plus 1. Right max at I plus 1, that's 5. So the max between 7 and 5, that's 7, right? So this is our right max. Okay, so now that we have our right max, we will need to do the prefix. So we move I now from left to right, and we do the prefix. Okay, so let's do our prefix. So we have prefix sum is going to be equal to 0 first, right, before starting. And now each time we want to have the best edges sum. Edges sum basically means it's a combination of a prefix and a suffix. And so our best edge sum, initially, let's just put it at minus infinity so that any value can be the max, right? And so what is the prefix sum when we do this one? It's 5, okay? And so what do we need to do? We need to do the prefix sum at I, which is 5, plus the max sum of a suffix that is at I plus 1. So I plus 1 is equal to 1. So what is the max sum at I plus 1? It's 5. So between 5 and, so we need to do 5 plus 5. That's so the edges sum is going to be 5 plus 5, which is prefix plus suffix. So that's 10. Is 10 better than minus infinity? Yes. So let's put 10 here. Okay. And then we move our I pointer here. And so we add minus 3 to 5. So now our prefix sum is 2. Right? And so what is our edges sum now? So our edges sum is going to be the prefix sum plus the max right sum at I plus 1. What is I plus 1? I plus 1 is 2. What is the max there? It's 5. So this is 7. Is 7 better than 10? No. So we keep 10. Okay? And at the end, we want to do the max. So at the end, this is the max. But remember, this was just this case. So we need to compare, just in case the max sum was one of these cases, we need to also do the normal Cadena algorithm that calculates the normal case. Okay? But you can see now that for an array that has this case where the maximum subarray sum is a combination of a prefix and a suffix, this method will solve it, right? So now we just need to think about, okay, what is the Cadena algorithm we can apply for the original case of just like normal subarray sum, right? Normal max subarray sum. Well, that is pretty easy, actually. Cadena algorithm is pretty easy. The only thing you need to think about a little bit is if it's one that has no empty subarray allowed or not. So in this case, no empty subarray allowed because it has to be non-empty. That's what the problem says. Okay? And so here, what does that mean? So what we can do, let's take the first example because the first example, the max sum is actually minus 2. The max sum is actually in the middle. It's a normal one, okay? So for this case, what we can do for our Cadena algorithm is just have a current value and have the best, where we store the best sum so far, okay? And so a current starts out, takes 1 first. And so this one, let's say maybe we initialize it to infinity, minus infinity, so that any max is better. And so we get 1. And so what we do basically is for current, we take the max of the number we are looking at and of current plus the number. Why is that? So either the number makes the whole sum smaller, or it's better to take it alone, right? So in what case it's better to take number? Let's say the number was minus 3 and the current sum was minus 2. And so if the current sum was minus 2, then minus 2, this is minus 5 and this is minus 3, so it's better to take minus 3. What is right? So let's say we had an array like this, right? With maybe some elements here, some elements here. But if the current value is minus 2, the current sum is minus 2, and we are looking at minus 3, which one is better? Is it better to take this subarray or to take this subarray? Or even maybe I can do minus 3, minus 2. It's better to take this subarray with minus 2, right? And so that's why we do the max between the number and the current plus number, okay? I hope that was clear, but this is just the Cadena algorithm, so you could just brush up on it. And the best is just the normal sum. It's just going to be the max of best and the current sum each time, okay? And so we did this one, we go to minus 2. Now the current sum is either minus 2 or 1 plus minus 2, which is minus 1. Minus 1 is better, so we put minus 1. And so is minus 1 better than 1? No, so we leave it as 1. We go to the next one, which is 3. So either we do 3 itself, or we do -1 plus 3, which is 2. Well, taking just the number alone is better. So you can see this is another case where taking just the number is better. By the way, if empty subarray was allowed, this formula will change a little bit, where we would have 0 here instead of number, right? Because it's always better to take 0 than a negative number, right? Okay, so now with 3, so 3 and 2, which one is better? 3 is better, so the current sum becomes 3. Which one is better, 1 or 3? 3 is better. And now we'll look at -2, and so here it's between -2 and 3 plus -2, which is 1. 1 is better, so our current sum is 1. But is 1 better than 3? No, so we keep our best as that one. And this is how we will find the normal case. So we have two cases, either this one, this case with the edges, or this one. So which one should we take? Well, we want the max, so let's just take the max. So we take the max of this best one. You could name it normal, best, or whatever you want to do. And of the edges, the best of the edges sum, right? So the best of the edges sum. Because we don't know if our array has this prefix and suffix thing that takes advantage of the last element being connected to the first one, or if it's the normal case. And so we do them both and take the max, right? Now we could either choose to do them both in separate loops, or we can combine the for loops of the prefix that we do here, because each of them takes I from 0 to n. So we can, for calculation of the right max, we would have to do it separately, because for the prefix sum we will need it. But for prefix sum and the Cadane one for the normal maximum subarray sum, we can do that in the same loop, right? Yeah, I hope that was clear. The main concept here is pre-calculating the right max, and then from there it's easy to find by going just the prefix plus the max suffix each time. And that will cover this case, and then the normal case is just Cadane's algorithm. Yeah, so that's pretty much it. Let's code it up and make sure it passes. Okay, so let's code up this solution. So we need n length of numbers, right? And then we need a right max, as we said, which will keep track of. So this is the max, basically the max suffix sum for the subarray starting at I. Okay, so by the way, this is right max at I. By the way, it doesn't have to be actually starting at I. It can be starting at I plus 3, but in that subarray, this value would be the max right one, the max suffix sum. Okay, so now we already know that the last position, right, which is n minus 1, the suffix sum is just that element, right, because there is nothing before it. And so now we just need to keep track of the suffix sum. So the entire suffix sum ending at starting at I. So this is going to be n minus 1. So this is basically suffix sum starting at I. And now we can just go for I from n minus 2, because we already calculated for n minus 1. And we go down like this. And so the suffix sum is just the cumulative sum from the end up to I, right? So which means each time we need to add the element at position I. And then we need to fill the right max. So right max is going to be at I. So at I, we either take I and include it in the right max sum, or we just go from whatever was the maximum sum at I plus 1. And so it's either the suffix sum, which means we include the current element, we include the number at I, and that gives us the maximum sum, or it's whatever max we had at the previous position, which is I plus 1. Okay. And that's pretty much it for pre-calculating the right max, the suffix sum, the max suffix sum. And now we just need to do it for the prefix sum, which starts out as 0. But we also want, as we are doing the prefix sum, we want to just do the edges sum. The edges sum, which starts out as 0. And we need, since we are doing this, we can also run the run Kadane's algorithm. But first, actually, let's do them in a separate loop first, just so that we make sure we understand this. So for the prefix, the best edges sum, it's going to be first, we are going to say prefix sum each time, similar to suffix sum here, is going to add the element at this position. And what is the best edges sum? It's just the sum, it's just the max of whatever we found previously best. So basically, edges sum, let's call it. What is this going to be? This is going to be prefix sum plus whatever was the best value, the maximum sum on the suffix side, but we need to maintain that it doesn't overlap. So, which means we need to start from I+1 so it doesn't overlap with the prefix. Okay, and this is what we are going to compare against. Now, there is only one caveat here, is that if I is equal to n-1, right, then there is no right max at I+1, so we should just consider the prefix alone, right? And so here, if I+1 smaller than n, then we are going to do just maybe say edges sum is equal to prefix sum. You could do that. But actually, if you do this, this is actually the same. This means basically the entire array, right? And so this is actually the same as the one we'll calculate for Kadane's algorithm, and so we don't need it, right? Okay, so we have the best edges sum for our second case. Now we can do Kadane's algorithm. So Kadane's algorithm just needs the best and best max and current. And so 0 and the max is going to be minus infinity, and actually similar thing, we need similar thing here. And it's just going through I, similar to what we did for the prefix, range of n. And it's going to be current is equal to max of the number, right? Just the formula for Kadane's algorithm. So the current sum is going to be just the max of the number and the current plus number. We already went through that. And then the best max is going to be just the max of best max and current. And so what do we need to return? Is just the max of both cases. The max of this normal array where we don't take into account that the last element is connected to the first one, and this one where we do the edges one. And so we just take the max of both. Like that. So let's run this. Looks good. Let's submit. Looks good as well, right? And now let's just simplify our solution then a little bit. So these two, it's the same loop, so we actually don't need a separate loop, so we can just move this up here and get rid of this, right? And just we return the max. Okay, so let's run this. And this works as well, right? Now here, this is actually just, we can simplify it like this. And that should be it actually. Let's run this. And this looks good, right? So just one thing to caveat here is that the time complexity, of course, is O(n) because we are doing just these two, each of them O(n). So O(n) time, but actually we are using O(n) space for this solution because of this right max. Because of this right max array that we are using here, right? Now the solution with that is O(n) space. I'll just give you a short indication of what it is like, but it's explained a lot on Leetcode, so feel free to take a look. But the idea there is that to get this best edges sum, right? All you need to do is find the minimum subarray, because it's always better to, because for the edges, we want to remove some part of the middle. And just to maximize this value, it's always better to remove the smallest possible middle part, right? And so you can use Cadence algorithm to calculate the middle part, minimizing it, and then that way this best edges sum is going to be just the total sum minus that middle part that we are removing. And then basically this is going to be just the total sum minus the middle part, which is going to be the min array, right? And that's the idea. Actually, I can just code it up quickly here, so that we can get a no of one space solution. And so the best edges sum, so we don't need the right max because we are going to calculate this best edges sum differently. So all we need to do is find the best min, which is the minimum middle part. That's what we are looking for after. So this is going to be max then. And so our best edges sum, we don't need a prefix sum. And so each time we so this is, let's call it current max, just so that they don't have the same name. And this is going to be current min. So this is current max. And this is going to be current max. And to calculate the current min array, that's just going to be similar, except here is going to be min. And a similar thing for the best min, right? It's going to be this, and the current min, right? So this will give us basically the middle part, the minimum subarray, okay? So to get the best edges sum is going to be just the total sum. So it's going to be just the sum of the numbers minus the best min, right? Why is that like? But intuitively, I think it makes sense because we have the prefix, we have the suffix. So this is the best edges sum we are looking for. And so we just want to subtract at least one element here, because otherwise it's just the same first case, right? Which is the entire thing. But we want to subtract something here such that this thing here is maximum. And so intuitively it makes sense to subtract the smallest value possible, right? The other way to look at it is the total sum is actually just this edges sum, right? The best edges sum plus the min, so this would be the max edges sum, the min inner sum, right? And so that tells you already that the max edges sum is going to be equal to total minus the min inner sum, right? And so the max edges sum then is, which is the best edges sum here, is going to be just the total minus the best min, because that's the minimal possible inner sum we can take, right? And so we take the max of the two. I hope that was clear, but I think it makes sense intuitively. Okay, let's just see. Yeah, total sum is going to be just the sum of the numbers. So we can just actually just take this, put this here. So there's only one use case here that we need to think about handling, and that's if all negative, then the best max is going to be negative. And so in that case, we just want to return that instead of, because it's just one element, which is the smallest possible one in the array, right? And so we want to return best max. If this is negative, that means the solution is just a single negative element, and so we want to return that. So this is just one edge case we need to handle, but other than that, this should work. So let's submit. Okay, so that looks good. Now this is better in terms of space complexity, but it's just a little bit, I think, harder to understand. I hope my explanation made sense though. So in terms of time complexity, this is O of n. In terms of space, we are only using extra variables here, so it's O of n. Yeah, the other smaller thing you could do here is just go through the numbers, since we no longer need the index, so you could just do number here, but that's not really a big deal. Yeah, so this solution is O of n time of one space. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.